Find all zeros and write the linear factorization. So f of x equals 6x to the fourth minus 7x cubed minus x squared plus 67x minus 105. Now I have to do PRZs here. And if I were doing PRZs here, I would probably graph it and try to find one to start. That would be a good start. Did anybody find one? Anybody? It's a fraction. Three over two. Thank you. 6, negative 7, negative 1, 67, negative 105. Right, keeps messing with my board. 9. Is that right? 6, 18, 9. So that would be gross 2. Oh, 3, 2, 3. 64, 32 times 70, sorry. Half of 70 is 35, and 35 times 30 is 105. All right, so this factors as x minus 3 over 2 times 6x cubed plus 2x squared plus 2x plus 70, and I can definitely take a 2 from everybody. X minus 3 over 2. Hey, what did y'all win? What did y'all do? Y'all won $10 a piece or $10 together? Oh. So what was y'all's TikTok? Y'all have to show me the TikToks. Okay, so now I'm at this polynomial that I'm going to have to PRZ again, and since y'all aren't talking to me about which factors work, I'm going to graph it myself. Oh, thank y'all. Negative 7/3. No wonder you. Positive 7/3. And look at a place, yeah. Yeah. I did it. Okay, so the one of the ones it was bad and I had to go back and redo it, but I redid it in third block, so the recording is right. No. We started that and then I said, "Yeah, we're not going to do it." Yes, it's the right. It should be the right recording. Canvas. A negative and a negative is a positive, so 6 divided by 3 would be 2, and times 7 would be 14, and 15 5 would be 5. Yes, it works. So now I have 2 times x minus 3 over 2 times x minus 7 over 3. This is a plus, y'all. No, it's not. No, it's not. No, it's not. No, it's not. This is a plus. Sorry. Brett, do not. 3x squared minus 6x plus 15. If I take out a 3, that makes 6 up here. This was a terrible problem. Multiplies to 5, but adds to negative 2, so that's a quadratic formula. Remember the goal? What am I trying to do here? I'm trying to get down to what? Not the zeros, but linear factors. So I just want factors that are linear. This is a quadratic factor, so I need to get it broken apart into the two linear factors that it is. And so to do that, I have to find the zeros, right? So now I'm going to use quadratic formula. Opposite b plus minus square root of b squared minus 4 times a times c all over 2a. And I'm just going to write this out here. 16 minus 20 is what? Negative 4? Yes, Miss McGee. That's not 16, that's 4. 4 minus 20 would be negative 16. I'm getting my numbers all back. All right, so square root of negative 16 is what? Y'all can do this. What'd you say? 4i. And I could technically divide all these by 2, just to make it a little easier as I write my linear factor. 1 plus or minus 2i. So now I have, so remember this is 2, right? This is 1 minus 2i, and this is 1 plus 2i, which ironically enough are what? What are those called? Conjugates, complex conjugates. So now I have 6 times x minus 3 halves times x plus 7 thirds times x minus 1 minus 2i, x plus x minus 1 plus 2i. Does that make sense? That's it. So to find the linear factors, we did have to find the zeros here. Yes. Well, in this case, since they're conjugates, it wouldn't really matter if you didn't, because you end up with the same thing. But you want to be in the habit of doing that, because this is the zero. That whole complex number is the zero. If I got to this point and it would factor, I could just factor it down into the two factors, and I wouldn't have to do all the other. The only reason I had to do quadratic formula here was because that wouldn't factor. Yeah. Yeah. This is all one problem. Not many. This was, yeah, like 6. I think it was 6. But you also had like 30 minutes in class to work on it. And they weren't all this difficult. This one was the one that, I mean, so a couple of them had quadratic formula. They shouldn't have all had quadratic formula, right? A lot of them you just factor down. Anything else? Y'all good? Which one was what numbers was it? 37 through 41. Yes, you just factored that completely. So if it didn't factor all the way, you didn't have to do quadratic formula. So like 37, no, that was not linear. It said linear and irreducible quadratic factors. So if it got down to a quadratic that wouldn't factor, you could leave it at that point. So like 37 got down to, let's see, it started x cubed minus x squared minus x minus 2. And you could get it down to this when you found the PRZs. Since this won't factor anymore and it's a quadratic, you can leave it right there. Y'all see the difference though in factored completely versus linear factors? Anything else? We'll get to the fun stuff today. Do y'all need a little break before we start? PRZs. I don't mind the PRZs. I am not a fan of the linear factorization. I can do it. I don't know. Have I not given you all yours back? Oh, I always. What does this word mean? Fractions. You're exactly right. Good job, Ty. Fractions. A number that can be expressed as a fraction or the ratio of two numbers. Please. No, that's rational thinking. What is a rational number? Okay. Oh, as a what? As a what? What was that you said? Expressed as a what of whole numbers? A ratio. What does ratio mean? Oh, maybe we need to look that up because ratios can be expressed as fractions. Okay, how do we express ratios? As fractions. Are you done now? You're being quite contradictory today. It's gonna happen. A rational function can be expressed as one function divided by another function. Brett, why are you so... I don't even know. Tell us when you're ready, please. By all means. This is Brett's world. We just live in it. Might you think that you encounter some domain problems with rational functions? That's exactly right. We can't have the bottom equaling 0. That causes us to have a domain restriction. Okay? And we'll talk about what those restrictions look like and what it might be. Let's talk about asymptotes for just a minute. What is an asymptote? Okay, it approaches something, it gets really, really close, but it never touches. Do you agree with that? So the graph really close. There is. I'm glad you said that, Brett. No, I can tell you. This is in layman's terms. Simple. No. Let's look at a vertical asymptote first. Brett's right. There's got to be a better definition than that, and there is. And it's a definition that we're going to use limits to define. We've talked about limits, right? The limit, when we described in behavior, we talked about limits. So I want you to think about a vertical asymptote on a graph. In fact, we'll just think about this parent function that looks like this. What function is that? Reciprocal function, right? 1 over x. Is that a rational function? Yes, it is. It's it's in fraction form, it's a rational function. Do I have a vertical asymptote here? Where is it? Give it to me in the form of an equation. X equals 0. Is everybody okay there? What if I asked you, what is the limit as x approaches 0? And I'm going to add this little sign here. What do you think that means? From the left. That's exactly. This means the limit as I approach 0 from the left of, and we're saying f of x is 1 over x. All right, Adam, what did you say it was? The limit as x approaches 0 from the left. Negative infinity. Why? It's going down and it's getting closer and closer to negative infinity. Does everybody agree with that? How about the limit as x approaches 0 from the right? It's infinity. So from the right side, I'm going up. From the left side, I'm going down. Both of them approaching infinity. Do you agree with that? Yes, no, maybe so? Maybe so. If you have one of these scenarios, notice I told you that we know our vertical asymptote is x equals 0. This is the definition of a vertical asymptote. So a vertical asymptote is defined. I want you to see it first. If you have a situation where the limit as you approach some number, and it doesn't matter what that number is, but it's just some value, we'll call it a, from either the left or the right, if you get an infinity, so in other words, as you get really close to that number from one side, it can be just one side, it doesn't have to be both, then you have a vertical asymptote there if you go to infinity. So if you go down real quick or up real quick, that is the formal definition of a vertical asymptote. Do you understand why, though? You look at that reciprocal function. If there is a number, I should have said this, is no. If x goes towards a number, if you get close to a number and the closer you get to that number, the graph goes up to infinity or down to infinity, that is a vertical asymptote. For example, let me show you another example. That because you said that wasn't a good, the definition I gave you before wasn't a good definition. So I gave you the mathematical definition. Mathematically, the definition of a vertical asymptote. Okay. Okay. Appreciate that. Everybody okay on vertical asymptotes as of right now? We'll go a little bit deeper in just a minute, but for right now. There is one for horizontal also. Let me, before I jump to horizontal asymptote, let me show you how to find it algebraically. This is graphically. Mm-hmm. Now algebraically, because this one we're looking to see if it goes a certain way because you haven't learned to evaluate limits yet, and you won't do that until probably, unless we get to it in here at the end, it'll probably be calculus before you evaluate limits. Let's say I give you, and this works with rationals. Let's say I give you is that a rational function? Yes. Without graphing it, do you see any problems I may have in the graph? I know that in my domain, and this is something we talked about before, x can't be what? 2 or negative 2? 2. You're looking at which one would cause me to have a 0 in the denominator, right? This actually means that I have a vertical asymptote at x equals 2. So here, how do I tell that this is a vertical asymptote? What we do is vertical asymptotes happen when the denominator this is what we call a non-canceling term, okay? Because I could have something, I'll give you all a second to copy that and then I'll explain what I mean by that. I'm gonna show you in just a second. Let me do this. Maybe instead of 1 over x minus 2, I had x minus 2 times x plus 1 over x minus 3, x minus 2. And here's my rational function, okay? Yeah. Based on what I told you, where do you think the vertical asymptote or vertical asymptotes are? 3 and 2 is what you initially think, right? But do you agree that that could cancel? This is what I mean by canceling term. So x equals 3 is my vertical asymptote. Even though here x cannot be 2, right? Do you agree with that? It can't be 2, but it's not an asymptote because it cancels in the top and the bottom. What this tells me is x equals 2 is a hole in the graph. Remember we talked about removable and non-removable discontinuities, and we talked about what a hole looks like? This is how you come up with a hole in your graph. There would just be a hole or 2. Do you see the difference there? If it cancels out, it's a hole, so we call it removable, because I could remove that piece from the equation, right? We call it a removable discontinuity, and it's a hole. But if it doesn't cancel, then it's a vertical asymptote. Does that make sense? Y'all okay there? A couple people are shaking their heads and a couple people are squinting at the board. So if it, let me think how I can word it. If the factor cancels, it's a hole. Say when denominator equals 0. The factor does not cancel, it's a vertical asymptote. It's still not a part of my domain either way. Either way, if I were to write the domain of this, I would have to leave out both 3 and 2. but they're different types. Does that make sense? Y'all do this if it does, and this if it doesn't. Give me something instead of, okay. Brett. Yes. Yes. So the very first example, x equals 2, was a vertical asymptote. I mean, like in this purple one, see how the x minus 2 canceled in the purple? That means there was a hole at x equals 2, but there's a vertical asymptote at x equals 3. Okay? Let's do one more example, vertical asymptote. Tell me if I have any vertical asymptotes or holes in this function. What are you going to simplify? What are you going to do? I'm going to try to put it in linear factors. You're exactly right. I'm going to try to factor it. Because I need to know, does it cancel out or does it not cancel out? Brett, what are you laughing at? That is the top factor. Oh, this is a terrible example. Brett, you are distracting me. That's okay. We can still do it. That is. This is factor. Do you agree? What? Would what be x minus 1? I thought x plus 2 1 is so what multiplies to positive 6 but adds to positive 5? 2 and 3. No, you keep them here. They're not zeros yet. They all don't. This still, that vertical asymptote is going to take over there. And it's still going to be vertical asymptote. Well, if you have a hole on a vertical asymptote, it really doesn't matter if there's a hole there or not because there's nothing there to take a hole out of. Does that make sense? So this one would actually be a vertical asymptote. I was trying to make you factor and trying to think of one that had the same factor, and then I put the same factor in there twice, like a dummy. You are not going to be, well, no, I lied. So it's a vertical asymptote here for -2. Because it was removable, but even if I remove it, that asymptote still stays. So it's going to be a vertical asymptote. No, because it's only when the denominator equals 0, not the numerator. What do you mean? Okay, so it doesn't. We're going to talk about what the top means when it equals 0. All right, questions about vertical asymptotes and holes before we move on? Are y'all okay? Let's talk about horizontal asymptotes. I'm going to teach you a little nifty trick for horizontal asymptotes. After I define them, Brett, could you not? Let's go back to our little friend, the reciprocal function. I'm ready to be done with this. I know that. What's the difference here? This is f of x equals 1 over x. When I'm talking about horizontal asymptotes, we defined vertical asymptotes. Looking here, I'm not finding the limit as x goes to a number for my asymptote. What am I doing instead? Where's my horizontal asymptote? On the... That's exactly right. On this one, I'm looking at my end behavior, because that's what's going to tell me about the horizontal asymptotes. I'm looking at the limit as x goes to infinity. And the limit as x goes to negative infinity. If this goes to some number, what did we call the other one? Did we call it A? Let's call this one B then. If you just go towards a value, in other words, if the end value, if the limit is I go to infinity, so if as I go as far right as I can go, if I'm getting closer and closer to a number instead of infinity or negative infinity, that means I have a horizontal asymptote at that point. So here, if I wanted to define this as the horizontal asymptote, well, the limit as x goes to, this is the definition, by the way. Well, then the limit as x goes to infinity of 1 over x is what? Look at this graph. It's 0. As I go further and further right, I'm getting closer and closer to 0. Does that make sense? How about as I go to the left? 0 again. These don't have to be the same. In this case, the horizontal asymptote bounds both ends of the graph. It doesn't necessarily have to bound both ends of the graph. It could just bound one end of the graph and still be a horizontal asymptote. This time I'm looking across. I'm looking at the ends. So this side is the limit as x goes to positive infinity, and this side would be the limit as x goes to negative infinity. And because it's getting closer and closer to a number, that number is my horizontal asymptote. Okay? So again, that's a graphic approach to the horizontal asymptote. Are y'all okay? Promise I'm going to quit talking soon, because I can tell by the glazed look some of you are like, what the heck? Try to make y'all a little cheat sheet tonight too. I think that we will stop just at asymptotes today. Algebraically, well, the first thing we have to do is identify any and all asymptotes, vertical, horizontal, and slant. There's one more that you've never seen before. These are all rational functions. Well, reciprocal is a rational function, but all rational functions are not the reciprocal function. Yes. No, you will be prepared. All right, algebraically, how do I find a horizontal asymptote? There are three scenarios that could happen with a rational function. Are y'all ready for this? These are the three you just have to memorize. I am going to look at the degree of the top and the bottom. What is the degree? What does that mean? The highest exponent. Scenario number one is I am bottom heavy. What does that mean? What do you think that means? The degree is bigger on the bottom. Okay? For instance, the reciprocal function is a bottom heavy function. If this happens, then your 1 over x, this would be a degree of 1, this would be a degree of 0. Because it'd be x to the 0 power. It's a constant versus a linear. Things like, it may be easier for you to see initially, x squared plus 3x plus 2 over x to the third minus 1. That would be a bottom heavy function. If that occurs and you are bottom heavy, now if you're in factored form, you're going to have to FOIL it out maybe to see if depending on how many, but you know how to look to add them together to find the degree, right? We've done that a lot. If it's bottom heavy, then the horizontal asymptote is 0 every single time. Everybody's favorite is top heavy. Not really, but top heavy is different because top heavy has no horizontal asymptote, but I have to check for what we call a slant asymptote. And there is more to come on this, but I do want it in your notes that you have to check for a slant asymptote when you see top heavy. And then the third scenario, what do you think it is? I've got bottom heavy, top heavy, equal, if they are the same. If they are the same, then the horizontal asymptote is the leading coefficient of the top divided by the leading coefficient of the bottom. Oh. For example, if I had y equals where's the horizontal asymptote? About vertical asymptote. This is not going to factor down with a perfect factor, by the way. a perfect linear factor. So what I'm getting at is you're not going to have a canceling linear factor here. So what would your vertical asymptote be? Any guesses? Close. If I have 2x cubed minus 4 equals 0, nobody? You're close. The cubed root of 2. Going to solve it all the way down for x there. Does that make sense so far? Yep. And as long as there's not a factor in the top that cancels with that, because remember that would form a whole. I really need to show y'all slant. Slant's easy. I'm going to show it to you real quick. Oh, I need to show you though. I need to at least show you. It's easy. Yeah, but you can't, you have to identify, all the homework involves identifying all asymptotes, and that includes slant. Okay, just quickly, slant. So this is whenever I have a graph where the asymptote looks something like this. And so my graph would come up and hug the asymptote, maybe something like this. But this occurs only in one scenario. It occurs when I am top heavy only. If I can spell it. To find the equation for a slant asymptote, are y'all ready for this? You do long division on the rational function, but you do not include the remainder. Whatever you get when you do long division minus the remainder is the equation of your slant asymptote. I'll do one quick example because it really is quick. Let's say I have that's a 3. Do I have any vertical asymptotes here? And -3. I got both, right? Do I have, all right, so how'd you get that? Tell me, for those that don't know. I do x squared minus 9 equals 0, so I got x equals plus or minus 3. Everybody okay there? Do I have any holes? No, I don't have any holes because they don't cancel out. Horizontal asymptotes. It's a slant. So there's no horizontal asymptotes, but there is a slant asymptote. So what I have to do is I have to divide. I have to say x squared minus 9 goes into x to the third how many times? And I can put my placeholders in here. X squared times what gives me x to the third? X. It doesn't matter. Minus 9x. This is my remainder. Do you agree? That is not even relevant. I'm sorry. That means that this, what's up top, is my slant asymptote. You can long divide, you can find the slant. You ignore the remainder and just take what you get when you divide. So this particular graph has 3 different asymptotes. It's got at plus or minus 3, and it's got a slant at y equals x. The line y equals x. So if I graph this, and I'll just graph it quickly, x to the third divided by yes, always. You see my asymptotes there? I've got vertical. Do what? So it can. Asymptotes can bound just a piece of the graph. It doesn't have to bound the whole thing. So the vertical asymptotes are bounding these middle pieces, right? And the slant asymptote, do you see it? Oh, it slants there. All right. I'll post your homework. I'll put it on the Miro board, but I'll post it also.